Up to this point, your study of calculus has been all about differentiation. If I give you a function, say f of x equals x squared, then you should know that the derivative of that function with respect to x is 2x. It's worth remembering that the derivative of another function, say x squared plus 17, is also 2x, because the derivative of a constant is 0. But what if I give you a function h of x? Let's say h of x equals 2x. And I ask you to undifferentiate or anti-differentiate this function. What I'm asking you for is the function whose derivative is 2x. One way of approaching this would be to say that if differentiating x squared, x to the power of 2, produces 2x to the power of 1, then the antiderivative of h of x, we'll call it capital H, must be to the power of 2. Otherwise, when we differentiate h, capital H, we won't get that 2 in front. If, when you're differentiating a polynomial, you reduce the exponent by 1, then when you anti-differentiate a polynomial, you must need to increase the exponent by 1. Something else is happening, though. It looks like the 2 in front of the x in the function little h of x has gone missing in big H of x. Let's take a look at the power rule for differentiation and see if we can figure out what's going on. The power rule says that if f of x equals x to the n, then the derivative of f of x equals n times x to the power of n minus 1. Of course, we can also write this as f prime of x equals n times x to the power of n minus 1. Two things happen when we take the derivative of a polynomial term. One is that we bring the exponent down in front, and the other is that we subtract 1 from the old exponent, giving us a new exponent. So if we want to find the antiderivative of a function, we have to do those same two things in reverse. We have to add 1 to our previous exponent, and we have to divide by the new exponent. So let's come up with a reverse power rule for anti-differentiation. If we have a function, big F of x, that we know is the derivative of some function, then the function it's the derivative of, we'll call that little f of x, must have a power that is greater by 1, and instead of bringing down the exponent and multiplying, we're going to divide by the new exponent. We call this the reverse power rule for anti-differentiating a polynomial term. Let's pretend we hadn't done this problem here yet. If I give you a function, h of x equals 2x, and we can see that's 2x to the 1, then the antiderivative of that function, it's a polynomial, must be x to the power of 1 plus 1 divided by 1 plus 1. As with differentiation, we carry the constant coefficient down in front, and that means that our antiderivative is 2 times x to the power of 2 all over 2. If we cancel the 2's, we get x squared, which is exactly what we were expecting. There's something interesting worth noting here, though. Remember when we started this lesson, when we differentiated x squared, we got 2x. But when we differentiated x squared plus 17, we also got 2x. So we need to make sure that we're accounting for all the possible antiderivatives of 2x. We know that x squared is 1. We know that x squared plus 17 is another. In fact, another antiderivative of 2x is x squared plus 1. Another one is x squared plus 13, or x squared plus the square root of 3. You can add any constant to x squared, and when you take its derivative, you'll get 2x. How can we account for the infinite possible number of antiderivatives of 2x? If we could have any constant at the end of x squared, and when we take its derivative, end up with 2x, how can we account for this infinite number of possible antiderivatives? Well, the answer is that we just say that the antiderivative of 2x is x squared plus any constant. The constant could be 0.7, or as previously discussed, 17, or even 0. When you take the derivative of x squared plus a constant, you get 2x plus 0. So the antiderivative of 2x is x squared plus a constant, any constant. The thing is, although the constant could be 0, it isn't necessarily 0. The derivative of x squared plus 17 is also 2x. Whenever you take an antiderivative, remember to add plus c to the end. Okay, that's the basic description of what an antiderivative is. Let's take a minute to write out a formal definition, and then we'll do an example. Okay, here's our definition. A function big f of x is an antiderivative of the function little f of x if the derivative of big F of x equals little f of x for all x in the domain of little f. Here's what that really means. If little f of x is the derivative of another function, then the other function is the antiderivative of little f of x. Big F of x is the function whose derivative is little f of x. Now, if a function is not defined at some point, then you can't take the derivative of that function at that point. And that's all this last line means. You can't take the derivative of little f of x, so you can't find the antiderivative of big F of x if there's a point in the domain of little f that's going to be problematic. All right, let's do that example. If the function f of x is 3x squared, what is the antiderivative? What is big F of x in this case? Well, this is a polynomial term, so we can use the reverse power rule. And that says you copy down the coefficient, you write the x with a new power of 1 more than the old power, and then you divide by that new power. In this case, that's going to give us 3 times x to the third over 3, and the 3's cancel. So there's an antiderivative of 3x squared. But it's only one antiderivative. We were asked to find all antiderivatives of this function. One antiderivative of 3x squared is x cubed plus 0. Another one is x cubed plus 12. A third one is x cubed plus a half. To account for all the possible constants that could be in that position, we just add a plus c. Now, how can you check this? Remember that the definition said if the derivative of capital F of x was equal to little f of x, then capital F of x was an antiderivative. So let's take the derivative of big F of x. Here's the function we claim is big F of x, the antiderivative of little f. Well, the derivative of x cubed is just 3x squared. And the derivative of the constant, of course, is 0. We don't even need to write that. Since the derivative of big F is equal to little f, we have found an antiderivative. And specifically, we have found all antiderivatives because we've added the plus c. And when you differentiate plus c, when you differentiate any constant, you get 0. Let's try another one. Find all antiderivatives of the function f of x equals 1 over x. Well, we don't have a rule for reciprocal functions, but we can rewrite this as x to the negative 1. And just as with differentiation, the reverse power rule works very nicely as long as our function is made up of polynomial terms. So here I would propose that big F of x, the antiderivative, is going to be 1, because the coefficient is 1, times x to the power of negative 1 plus 1. And I'm going to divide that by negative 1 plus 1. When I simplify, I get x to the 0 divided by 0. Well, that's a problem, right? We can't divide by 0. The numerator here would be 1, but we can't divide by 0. So we have to do something else. In fact, what we're going to have to do is recall some of our derivative rules, some of our derivatives of standard functions that we worked with in differential calculus. You may remember, or you may not, that the derivative of the function the natural log of x is 1 over x. And I'll need to remember that going forward. So since the derivative of ln of x is 1 over x, the antiderivative of 1 over x is ln of x. Now that's an antiderivative. If I want all antiderivatives, I need to write plus c. Can we check this? Sure. What's the derivative of ln of x? It's 1 over x. And what's the derivative of c? It's 0. So we have in fact found the general antiderivative for 1 over x. Let's do another one. If f of x equals cosine, and we're looking for the antiderivative of cosine, then we need to ask ourselves, whose derivative is cosine? And I hope that you remember that the answer to that question is sine. Since the derivative of sine of x is cosine of x, then the antiderivative of cosine of x is sine of x plus c. Let's do another one. If f of x is e to the x, what is the antiderivative of that function? Well, remember that the derivative of e to the x was e to the x. So the antiderivative of e to the x is e to the x. But the antiderivative of e to the x could be e to the x plus 17, or plus 1, or minus 3. So an antiderivative of little f is e to the x, but the general antiderivative of little f is e to the x plus c. Differentiate that, and you get e to the x plus 0. So this is the correct antiderivative, general antiderivative of e to the x. Here's a summary of everything we've talked about so far. If you have a polynomial term, its antiderivative is going to have a power that's higher by 1, and you'll divide by that new power. The antiderivative of 1 over x is the natural log of x. The antiderivative of cosine is sine, and the antiderivative of e to the x is e to the x. Don't forget, though, that every single one of these must have a plus c. The derivative of the sine of x plus any constant is going to give you the cosine of x. So the antiderivative of cosine is the sine of x plus some constant. Sometimes you'll hear it referred to as an arbitrary constant. It's arbitrary because we have no idea what it might be, at least not yet. But it has to be there. It's part of the answer. Without it, you're assuming that the constant is 0, and that's not always the case.